Good evening. So, as was mentioned, my normal area of research has nothing to do with planetary defense, except maybe trimming the lawn once in a while or letting it go dead to defend the planet against overwatering. But I got into this a couple years ago for reasons having to do with terrestrial kinds of threats, and then looked beyond to see what could be done in terms of planetary threats. And so I think it's worthwhile to actually look at this in a sort of a futuristic scenario. What could be done based on not wishful thinking, not miracle here, or we need this to be done, but rather what exists now and what is likely to exist in the near future. And so I'd like you to kind of open your minds a little bit, because this will probably stretch your boundaries. But some of it you'll see is extremely real. I'll show you some laboratory examples. And then I'll ask you to kind of ponder what will inevitably, in my opinion, come. It's not a question of if, but it's a question of when, in my mind. Okay, so this is a picture of a bit of artistic license for the recent Russian event. And the only reason I'm probably here, realistically, is because of this. And because, as I'll show you, we announced one day before Russia got hit in a press release. Okay, so let's just talk about this a little bit. So this really should be a discussion of directed energy or directed photonics, because there are many types of directed energy. But this is really photonic directed energy. And just some quotes, if you followed this area in terms of our concern about extraterrestrial threats. There's obviously been some attention to this. And had the event been over Washington, D.C., you could be assured that we would have as much funding as we want. Having been over Russia, it's somewhat less so. So there are two auxiliary talks, one which happened a few hours ago on beam propulsion, which is a secondary application, and then one tomorrow afternoon at 1 o'clock Gary Hughes will give on related topics. So, okay, so those of you that follow the internet know that every once in a while we get threatened by something, and usually we duck the bullet. Recently, end of May, there was an asteroid that came by that was fairly large and passed within a distance of about 4 million miles. And it was about 2 miles, roughly 2 mile size thing. And if you just work out the math, which will show you 2 miles coming in at typical 30 kilometers per second or Mach 100, if there was such a thing in space, would be a bad day for all of us. Okay, so what didn't miss was on February 15th, the same day that we expected to pass by what was sometimes known as 2012 DA-14, we got hit in Russia by about a 20-meter diameter asteroid. So a rock came in at about 12 kilometers per second, and it was an airburst at about 20 kilometers altitude with a kinetic energy equivalent to a strategic thermonuclear weapon, about half a megaton. If it had come in a little bit lower, a little steeper angle, we probably would have had tens of thousands, perhaps 100,000 deaths. Luckily, it just blew out a bunch of windows and was certainly a major wake-up call. In 1908, we believe about a 40-meter diameter asteroid came in and was a 15 megaton air burst at about 10-kilometer altitude. And since the 1970s to early 80s, there are about 140 what are called major atmospheric, upper atmospheric events, i.e. things coming in at very high speed. Okay, well, we've been studying this for quite a while, at least I have, and our group released a white paper on February 14th. So 18 hours later, I woke up and I thought, okay, well, DA-14's passing by, but instead Russia got hit. So the bottom line is, try not to release white papers just before something happens. Otherwise, you might get a lot of questions from the news media. So this is a map of the last 4,000 years of noted points of impact that we're aware of, and there's some close to 35,000. And they all happen to hit on the land masses, which is very clever of whoever's shooting at us. But of course, that's not true. That's where we find them. And on a given day, by the way, we get about 100 tons of material falling down on us. The reason we don't notice it is there's a difference between taking 100 tons and shredding into little pieces and letting it fall through the atmosphere versus one single 100-ton asteroid, which would be an event worthy of the news. So I'm going to just blast through a lot of things for you. If you have questions, ask later or ask Gary tomorrow. But there have been a lot of what we believe are large-scale impacts leading to significant destruction of life on Earth. And as you may know, about 65 million years ago, the dinosaurs had a very bad day and went to sleep for quite a while. But at least they perhaps gave us our hydrocarbon age. And that yield was about 100 teratons. So a teraton is a trillion tons of TNT. A typical strategic weapon is a megaton. So there's 100 million megatons. So that's an existential threat. That, we believe, was a 10-kilometer diameter asteroid or comet, and it made a crater about 300 kilometers on the Earth, which is largely underwater, so it was never noticed for a long time, but is now thought to be towards the southern tip of Baja area. Okay, anyway, just some other numbers. Chesapeake Bay is about an 85-kilometer crater. Largest known volcano has yielded about 240 gigatons. And this is a plot here, which is, I don't expect you to read it, but versus time from zero. So this is 50 million years, 100 million years. Here's the 65 million year extinction. This is the fraction of all life extinguished on Earth as a function of time from t equals 0, which is now going backwards. So at this point, we lost about 35% of all known life forms. Okay, so there's a lot of material out there. The typical closing speed is between 10 and 60 kilometers per second, which is quite fast. But they tend to be fairly dark, having reflection coefficients around 5% or so, some 10%. Usually solid, well, some solid, some rubble pile, some other things we're not quite sure of. A lot of them are carbon rich, they're silica rich, metal types, typical temperatures at the distances they're out are of the order of 200 Kelvin or so, which is important for detection. How do we detect asteroids? Well, we of course go to our Congress and we say, please detect them for us. So they mandate detection, which just imagine, being in a lab and Congress mandates what you have to do, not just by funding you, but saying you shall detect 90% of all asteroids greater than 1 kilometer. And you said, okay, yes, sir, just give us the money. So that's now largely been done. NEOWISE, which has been recently re-energized, detected, we believe, about 93% greater than 1 kilometer as of the end of last year. And if you follow the media, the B612 Foundation is building upon a previous NASA mission to go after thermal infrared imaging, which will hopefully add even more to our knowledge of asteroids, because understanding where they are and what their orbital parameters are is critical. Okay, so NASA has reactivated a previous infrared survey, the WISE survey, which is incredibly successful, but unfortunately it ran out of solid hydrogen, and therefore the long wavelength channels no longer work, but the shorter wavelength channels still do. So they've now recently, as of a couple days ago, NASA has accepted a proposal to reactivate it. So this will be used for future missions, a future mission to look at some near-Earth, potentially hazardous objects. So NEAs or NEOs, near-Earth asteroids or near-Earth objects, are distinguished from PHAs or PHOs, potentially hazardous objects or asteroids. And it's a somewhat awkward nomenclature, but they have a similar Earth-crossing orbit as is shown here. And I think Gary tomorrow will show you this beautiful movie of the detection of asteroids versus time, versus how we look for them. And you see this amazing blip coming in as we ramp up sky surveys. Of course, this is going to take off as LSST comes online and other surveys go after them. So knowing where they are, how many there are, and their precise orbital parameters is absolutely critical. So there's a beautiful census from the NEO-WISE effort, just looking at objects that are various size categories greater than the kilometer, 500 to 1,000 meters, et cetera. And as you go down the chain, you become increasingly uncertain as to what's out there. And I'll show you in a minute that things in the few hundred meter class are still quite dangerous. They're not existential threats, but they are, could be important, particularly if they land on a city. Okay, so NEO-WISE, which is a cryogenic mission, as I mentioned, used Mercad telluride from about 3 to 22 microns. And they were incredibly sensitive compared to what we had on COBE. On the Derby mission, they were about 500,000 times higher mapping speed. So they observed about 160,000 rocky bodies. There's different, again, nomenclatures for things. Of about, we believe there's about 600,000 which are known. But this is, obviously there's a distribution. So that distribution goes down to extremely small sizes. So this number is very arbitrary depending on the cutoff. They discovered a small number of comets, about 34,000 asteroids, and on the order of 100 plus near-Earth objects, and about 20 which are potentially hazardous, i.e. cross the Earth's orbit, it might be a hazard. As of last year, as I said, greater than a kilometer class, we believe we found about 90%, so about 911 were found. Okay, on the other hand, less than 100 meter, we estimate there's an order of 1 million or more, and we really don't know what's out there in that class. And we estimate between 100 meters and a kilometer, it's about 20,000. Okay, so it's going to be reactivated in a radiative cooling mode, so not nearly as sensitive, but still quite useful for the shorter wavelength channels only. So detection, if you look at detection versus time, you can see it's ramped up. So this is number detected versus year. So going back to 1980, and here's 2013. You can see it's ramping up very quickly, and these are because we go out and take our time to look for them. And this will ramp up even more, as I mentioned, with LSST and other missions. There's all kinds of distributions. Asteroids are fascinating for some people. For me, it's just kind of a side product what I do, but they are actually quite interesting in their orbital distributions and their compositions. So it's something you might want to look up. There's lots of material out there. This is a little picture of the Tunguska event in Russia in 1908, which Russia seems to be plagued by these things for reasons that are unknown. I'm sure from their side they must think that maybe it's a conspiracy. But if you want to look at relative threat levels, what kills you in life? Photonics, working hard in the laboratory is probably detrimental. I don't have that on the slide here, but I'm sure there's some threat level from being a scientist. One of your greatest threats in life is going out and driving in a car, which is you have about a 1% chance of dying during your lifetime from a car accident. And then you can work your way down the list here. Asteroid and comet impacts from a nature study in '94 were about 1 in 20,000. Of course, they're very episodic, which is similar to your probability of being killed in an airplane crash. That number's gone down a bit now that we've studied them more, possibly by a factor of a few, but it has to be looked at in more detail. And if you're worried about food poisoning, it's 1 in a few million. And if you write proposals, well, I'm sorry, but you could sue the government for destroying you. Okay, so I sometimes talk to DoD audiences, so I use a slightly different language, so I apologize, but they find it humorous. All right, so whoever's throwing these things at us has a very large stockpile of them. Right, has teraton devices, which are existential threats to us. Their tactical devices are in the megaton range, and they don't negotiate, and they actually prefer mutually assured destruction because every asteroid which is destroyed creates more ammo for them. They're very fast, up to 60 kilometers per second. They hit us every day, typically 100 tons a day on a slow day, and we don't know where they're coming from. Right? One of them has your name on it, and you may be dead when it has your name on it, but one of them does. It's going to happen again. It's happened in the past. It will happen in the future. Now, the good news is it's not a very intelligent enemy. So they don't have very good aim. So we normally just dodge the bullet. They have no guidance systems. They lack all countermeasures. They're deterministic. So once we figure them out, we can actually do something about it. And they show us everything they've got. They don't hide it in underground bunkers or put it on trains or hide it in houses. So we know what's out there. We just don't know what's out there. They have no strategy, and they don't evolve. It's not strictly true, but they don't really evolve much. Okay, so directed energy planetary defense should be considered. You shouldn't just laugh and walk away. You should actually think about it for reasons I'll show you. Okay, here's a plot of asteroid impact frequency. They come in. You can see here's the number per year on the vertical axis versus the diameter here. So here's Tunguska. Comes in, approximately, if my glasses work here, once every a couple hundred years, we get something of this class coming in, 100+ years. And these are, of order, say, 50. So if you've been in the Barringer crater out in, out Highway 10, I guess it is, out in Arizona, that was a similar class. And these are multi-megaton. Again, Tunguska is about 15 megatons. Apophis is currently thought to be about 325 meters, which I'll discuss more. That's in the gigaton range. So that would be a very bad day. The one that killed the dinosaurs is in the 100 million megaton range. Okay, so here's impact energy in megatons versus occurrence per year. So once every 100+ years or so, we get hit by about 10 megatons. So if we knew, I hate to pick on North Korea, but if we knew that every once in a while, every 100 years, North Korea would launch a 15 megaton weapon somewhere in the world, I'm sure we'd be a little bit concerned. And that's what's happening. Just we don't think about it. I mean, we have very limited forward thinking. Right? If I told you 100 years from now you're going to die, you'd say, yeah, I know that. Right? But if I told you 100 years from now 100 million people are going to die from an asteroid impact, you would say, oh, I guess we better do something about that even though I'm going to be dead. So we tend to have very limited memories. This is impact energy in joules and in megatons on this axis, joules on this axis, versus diameter for different closing speeds. Typical orbital speed is about 30 kilometers per second, which is the mean orbital speed of the Earth around the sun. So 100 meters coming in at 30 kilometers per second is on the order of, 100 meters coming in is on the order of a few hundred megatons, roughly. Okay? Well, so what we proposed was looking at this from a practical point of view. What could you do? You could send nuclear weapons out to hit them, which some of my friends, Lawrence Livermore, do, and I actually support that very much. You could send out spacecraft to ram into them and move them a little bit. You could send solar sails out. But we decided, was it possible to have a standoff system and then just basically do what you do in laser machining? Could you laser machine them away? So it seems preposterous to think about, but then we ran the math and found, well, maybe it's not so nuts after all. Okay. So the part of this draws from a DARPA program, which is developing high-power fiber lasers for applications not having to do with extraterrestrial threats. And that currently has now achieved about 35% wall plug efficiency. And they are phase lockable, which is key. So out of another program, we decided let's just look at scaling this up. So we just basically took the same idea and let's scale it up. Let's build a phased array and see what the consequences are. How large would you have to make a phased array to completely eliminate the threat of all known asteroids to the Earth? And I'll use the term all known, because we could get hit by another planet, which this would not take care of. But up to kilometer class, this would work. And we set a very strict and incredibly conservative goal of completely evaporating, completely laser machining away a 500-meter diameter asteroid in 1 year, which is sort of typical for distances of 1 AU or so, a few months to a year. And it's incredibly conservative, I'll show you. You don't have to do anything like that. And what we came up with is a very low areal density, less than a kilowatt per square meter. So the heat rejection, which I get questions on all the time, is not the problem. It's like your body. It's not much more than your body. It turns out to be about 500 to 700 watts per square meter. It's inherently multitasking, so you don't just need to do nothing with it until a threat comes along. You can use it for propulsion systems for spacecraft. You can use it for communication systems. You can use it to send power to the ground. You can use it to interrogate asteroids. It has all kinds of uses that you might imagine. It's big, yes, but it's completely modular, so you can build small versions and work your way up. So what makes this possible now to be a science talk rather than a science fiction talk? So tomorrow night I'm going to speak at the Arthur C. Clarke Center, and it'll be a little bit more futuristic oriented. But you know, 10 years ago, this would have been, I would have come into a talk like this and said, this is preposterous, it's just science fiction. We have no such lasers available. But we do now have such lasers available. You can hold them in your hand, you can buy them, and it's going to be a very scarier world soon when they're going to be in tactical weapons, which they will be, handheld tactical weapons. So the reason this is possible is basically photonics. The reason all of you are here is you're making this possible. You develop materials and devices which are incredibly efficient. You supply Home Depot with 50% efficient LEDs. You provide lasers which are incredibly efficient. You develop photovoltaics which are now pushing 50% efficiency. It's you that are responsible for this. So what's key here is to not go off on the imaginary axis and say, what if, miracle. No, it's to say what's real now and what could we do with it and what sort of technological advancements could we imagine. So the base idea is just take a beam, phase lock it to form a small spot, absolutely key. Can't just take a bunch of laser pointers, it won't work. Can't take a mirror. The other question I get, why don't we just focus the sun on it? Because the flux on the target goes like 1 over the square of the F number. And therefore, if you want to get to high temperatures needed to vaporize typical rocks, you have to build a mirror the size of the solar system. It doesn't work, at least in my mind. So the key is to make phase lockable systems. So the goal, again, was 500 meters in a year, and that requires a roughly 1 to 10 kilometer size system. So that sounds big, right? The space station, the biggest thing we ever built, is 100 meters in size. So 1 kilometer would be 10 times the size of the space station. It sounds hard. But you know, when you're talking about planetary protection, is that hard? If you go back 100 years and ask someone, hey, maybe we're going to go to the moon in 100 years and we're going to build space stations in space, you would have been laughed out of the room. But go forward 100 years or 50 years. Is it impossible to imagine building a kilometer class thing? I don't think so. Okay, so the spot size for such a system, if you build the largest one, which you don't need, would be 30 meters at 1 AU. And that's where we propose to begin interdiction. It's extremely conservative, and smaller systems work at closer ranges and are useful for things like space debris. So there are other mitigation methods, as I mentioned. You know, you can hit it with things. You can have a kinetic kill mode, iron thrusters, you know, strap on an iron thruster. You know, there's all kinds of things. Strap on a solar sail, you know, strap on some sort of propulsion system, hit it with a nuclear weapon. These are all required dedicated missions. Our goal was to not go for a dedicated mission for a threat, but have one standoff system. And that's the goal that we set for ourselves. So the common features of all the existing ideas are that you basically have to have a system for every threat, which is really a problem because you got to make sure that thing works, which means you're probably going to have to send 2 or 3 of them to make absolutely sure it works. And there's also a problem is that some threats are multiple threats, like the Shoemaker-Levy that hit, object that hit Jupiter had 21 fragments. Well, that would be bad for us if there were 21 individual fragments coming in. That means you're going to need 21 probably times 3 missions. That would just be, that would be bad. It would be hard to do such a thing. And they had sizes from 100 meters to several kilometers. So the previous, you know, it's not really the word in the dictionary, but there's a stand-on system. You have to stand on the target and do something versus stand off. So we proposed just to look at standoff as a possibility. So if you look at binding energy, which I won't bore you with, but you look at the amount of joules per cubic meter it takes to vaporize things, you find, of course, the gravitational part is tiny. It's the heat of vaporization, as you expect. And it's typically, if you want to remember a number, it's about 10 to the 10th joules per cubic meter to evaporate rocky substances and even to evaporate ice in comets, about 10 to the 10th. And then we looked at a variety of asteroids. We've run basically every element on the periodic table, so I'll show you a couple examples of. And we've run a number of compounds. We're continuing to go through lists, but basically they all are fairly similar, and we go for a very conservative analysis here. So again, this question, why do you doubly convert? You have photons from the sun, you're going to send out photons to the asteroid, you're insane. Why don't you just send the photons from the sun? And the answer is, it doesn't work. Okay, just classical optics, étendue, you know, Louisville theorem, A omega, it doesn't work. Okay. So if you look at a phased array system, the spot size is basically just, you know, 2 lambda over d if it's a square, or 2.44 lambda over d. You can do some classical optics, and we do more sophisticated stuff later. But You can just look at the spot size and the amount of power, assuming that the power is all solar power. There's no reactors on board, nothing. It's all just solar power. And the solar power is the same size, solar array is the same size as the laser array. So we just made them equal for simplicity. You could change that. So a class 4 system delivers about 1.4 megatons per day equivalent energy, but vastly more efficient than delivering a single 1.4 megaton weapon. So 1 EV photons, which are about a micron, actually more efficient than detonating a thermonuclear weapon, which is good at producing neutrons and X-rays, but not really as efficient as taking the energy in 1 EV photons. Okay, so take every element in the periodic table and compounds, things you do in processing, compute vapor pressure versus temperature, and you find everything goes by the time you get up to several thousand Kelvin. You all know that. We do this every day in the laboratory. So could we do it in space? So we modeled asteroids thermally, and I'll show you some detailed 3D modeling. You measure their thermal conductivity by various means. You find it's actually extremely low. It's lower than fiberglass. Why? Because they're rocky and they have point contacts, kind of like a carbon resistor. They tend to be, worst case, around 1 watt per meter Kelvin down to about 10 to the minus 4. Really highly thermally resistive. So then you calculate spot temperatures as a function of the array size at different distances. So here's the spot temperature. Here's 100. Here's 1,000 Kelvin. Here's 10,000 Kelvin. You just work your way up, and you find, depending on the distance away that you begin to interdict the target, you can easily get up to several thousand Kelvin at 1 AU. And if you just want to go after something like a comet, you can hit it at 10 to many tens of AU. And if you really want to be dicey and play chicken, you can hit it at 0.001 AU, but good luck. It's like watching the movie Melancholia, if any of you have seen that. It doesn't work very well at short distances. So here's the maximum distance to start evaporation for everything from a comet, which would evaporate pretty well at room temperature, to if you had a solid carbon target coming in, or a diamond asteroid, which would be interesting, or tungsten, which of course no such things exist to our knowledge. Anyway, you can take them out for rocky things, which is sort of worst case, you can take them out at about 2,000 Kelvin. You get huge vapor pressures. Okay, time to vaporize again, a year for 500 meters. We've run all kinds of cases. So these are some more sophisticated analyses. This is silicon dioxide, which is a typical component of an asteroid. Lots of different things on here. I'm not going to bore you with all of them. If you want to look at mass ejection in kilograms per square meter per second, it's the dotted curve here. It's largely exponential with temperature, as you might expect. Okay, and it reaches enormous numbers. And I'll talk about that in a minute. Now, if you plot it versus flux, which is more interesting, so this is watts per square meter at targets. Here's a megawatt square meter. Here's 10 megawatts a square meter. We operate in this region. You enter a linear regime where every additional watt you put in basically goes into mass ejection. And the temperature doesn't rise very much. It's like boiling a pot of water. No matter how high you turn the flame up, all you do is boil more water per unit time. You don't raise the temperature. Same thing here. This is the temperature line. It doesn't change very much as you go to high fluxes. But the mass ejection rate does change, and the vapor pressure does change, which means the thrust on the asteroid from the plume being evaporated changes dramatically. So just for reference, the thrust for a class 4 system is roughly equivalent to the shuttle solid rocket booster at 1 AU. Well, imagine strapping on a shuttle rocket, Shuttle SRB, to an asteroid, and ask yourself what happens. And the answer is you deflect it really rapidly, because you don't just leave it on for 1 minute or a few minutes like in the shuttle. You can leave it on indefinitely. It doesn't take very long to deflect it away from the Earth. Okay, so we built a little test in the lab just because students love to blow things up, as you know. I'm sure all you do too. So we basically have 19 lasers in a module. We're going to mount in fiber optics and then recollimate them back down. So this is our phasing system, if you want. It's not quite right, of course, but couldn't afford to build the real thing. So we rephase them with an optical element and then just hit a target. And this is what it looks like. And students love this kind of stuff. They've been there all day blowing stuff up. In fact, they love to blow stuff up so much they blow out our laser. So we built a system that gets up to 40 megawatts a square meter, which sounds impressive, but it's not that hard. The system that we propose is designed to go to about 50 megawatts a square meter at 1 AU, so it's about the same. So does it work? Yeah, it works incredibly well. You can blow holes through everything we put in front of it. And there's a little picture that shows some of the students. So they turn on the laser, and I told them, go get some sand from the beach, since we live near the beach, and let's just see if we can melt it. Well, silicon dioxide and sand does not have a particularly large absorption coefficient, but when they were done, which you can't tell here, and this is an infrared movie taken with a FLIR thermal imaging camera. The temperature actually goes, it's off scale, you don't really see the right temperature, is you end up with a melted sphere, largely spherical element of melted sand, which I just thought was fun. And of course they stick chocolate bars and, you know, their friends' iPods and everything else in front of there. I mean, the students just love it. I guess I would too if I were able to do that for all day. So we stuck them in front of a computer and said, hey, run a 3D COMSOL model. So just put in all the physics and, you know, crunch the numbers and see if it agrees with our simplistic analysis. And remarkably, it agrees incredibly well. So the mass ejection, here's temperature versus time. You see it rises, the overshoot's a numerical instability. It rises, then it hits about, in this case for SiO2, which is what this is for, about 2400 Kelvin, 2500 Kelvin. And then it stabilizes. So in 1 second, you begin mass ejection, huge amount of mass ejection, 20,000 kilograms per second. The density is low. You might worry about, does it get in the way of the beam? No, the maximum density right at the spot is 1/100th the density of air at sea level. Why? Because it's spread out over a large region. So the plume thrust, again on the Orbital shuttle, can divert any known threat, again, that we currently know of. Okay, so if you work out it's kind of a worst case, take Apophis, which is 325 meters, coming in at 30 kilometers per second. Just say, you know, what happens if you turn this thing on? Turn it on for a month. How much can you divert it by? So very simplistic analysis. You'd really want to do a proper analysis. The answer is you can divert it in 1 month, exposure, by about 50 times the distance to the moon. Enormous overkill. It's complete overkill. Right? So you can back way off here. You can use smaller systems, lower power. You can have a set of free flyers if you want. You just want a large baseline to get the spot small. You don't need this massive system, although it's useful for other things. And this is 300 meters is a big asteroid. And that a month, you could do this actually if you work out the math. If you want just 10 times the Earth radii, go down by a factor of 300. Go down from 1 month to 1/300th a month, which is 2.4 hours. And then you've deflected it. So it's not as crazy as you might imagine. So we put one of our students onto making a little animation because he loves video games. So this is tried to be as physically real as possible. The plume comes off at 1 kilometer plus a second. So it doesn't hang around like clouds might. The ejection happens within about a second. And I'll show you some interesting math in a moment as to why we're not so sensitive to things like beam jitter, et cetera. So. Okay, then we've done all kinds of analyses of 2D versus 3D fits for the thermal modeling, and all seems to work well. We looked at mass ejection rates for everything from 0.1 to 100 gigawatts. Then we looked at how well we'd have to point, because pointing is a major issue here, as you'll see. And the answer is, for higher power levels, you don't have to point very well at all. You can derate the size a lot. Why? Because you heat the surrounding material and you still have mass ejection. Works really well. Even for 20 times the diffraction limit, it still works well. Okay, and you can see for lower power levels, it doesn't work as well. For higher power, it does. Okay, and then we ran laboratory tests. These are the laboratory test simulations, then we compare it. We're about to enter into the vacuum phase of testing, but so far everything looks good. So you can use this system for a lot of this stuff. First of all, suppose I turn off the lights in this room and I'd say, I wonder where he is. Well, it might be nice to turn the light. So one thing we could do is use this system, which is a very narrow wavelength, to illuminate asteroids and then detect them in the narrow band, which drops the backgrounds dramatically. So you can use this thing as like a LiDAR system. You can beam power to spacecraft. You can send power to the ground. We've been talking to Pentagon and other people about that. And you can use it for spectral analysis, which we're trying to work through at the moment. So we've looked at roadmaps, and I'm not going to bore you with that, but one thing that's amazing is if you look at the current technology in ytterbium, which is sort of the baseline, because we wanted something real, the optical efficiency, the measured optical efficiency is 85%, roughly 85%, up to 87%, which is just amazing when I saw this. Current wall plug efficiency in the DARPA program is about 35%, and this will rise. It's currently limited by the pump efficiency, which is currently about 45% on in-gas. So we expect this to go to probably 70% in the next decade or so. The solid state power density will soon hit a kilowatt per kilogram, which is going to be scary. Just think about, you know, a liter, kilogram, kilowatt in your backpack. Just think about it. Coherence lengths look good. They're typically limited by the stimulated Brion scattering in the current systems, although there is a way to get around that. The current systems are up to about 2 kilowatts. We only need 1 per square meter, so it's not very challenging, actually. Anyway, if you want to look up how ytterbium dope amplifiers work, you can take a look online. They're just truly amazing devices. Here's the efficiency, measured efficiency versus pump power. The power output versus pump power in. It's about 85%. Here's what they look like physically. Here's one, which is a 1.5 kilowatt, and you can hold it in your hand. It doesn't take much imagination to imagine what one can do with this. And so this is used for other things, for programmatic issues. Here's hitting a target through the atmosphere, which will allow you to use your imagination. And it's harder here because you've got a turbulent atmosphere in space. We don't have much. We looked at the solar wind and other possible perturbations. The structural perturbations are the largest one. So here's some examples of smaller fiber arrays, not the way we would do it, but just real examples. Here's some beginning optical designs. If you take a small 2x2 array and just model it, here we modeled it nicely in collaboration with ZMAX. You can see here's 4 individual elements, 2x2. Here's them in pairs, and then you form the collective spot pattern. Of course, you see a lot of side lobe structure here. So as you go from 2x2 to say 100 by 100, that central spot's going to get almost all the power. Pointing stability, you know, how much of an issue is that? So this is a question. We'd like to have a spot which is a few tenths of a nanoradian. It sounds hard, but HST already points to 35 nanoradians, sort of dead pointing over 24 hours. Parcos went down to 5 nanoradians in reconstruction, and our beam, is about 0.2 nanoradians or 0.04 milliarc seconds. Sounds hard, but it's not crazy. If you followed the Event Horizon Telescope, which is an attempt to measure the event horizon in the black hole at the center of the galaxy, they already phase locked across the Earth, not at 1 micron, but at 1 millimeter, and got down to almost exactly the same point, 0.1 nanoradians. Okay. So you might take a look at that. Here's a phased array. Here's sparse phased array, very sparse. This is a Russian interferometry mission, which is also used in the United States. They get down to 0.04 nanoradians. Well, we're not anywhere near that, and they have huge baselines. So metrology is one of the enabling elements here, because you don't have to make a mirror which is flat to lambda over 10 in space. You have to know where the elements of the mirror are. So just if you look at LISA, their goal was 0.02 nanometers over 5 billion meter baseline. These are just examples. They're not exactly analogous, just examples. Of course, they got canceled. All right, JWST uses a different approach altogether. The JPL AMD program has achieved now 1 nanometer resolution. And I've talked to them. They've been in the loop on this. They think that we could do easily 100 nanometers, which is what we want, lambda over 10, over many kilometers. Suppose you want to point it at the ground. Well, obvious, interesting uses for it, some of which I won't discuss here. Some of them actually could be quite useful for geoforming, and I'm not talking about people. You could put it on an atmospheric line. So we looked at this for studies of how to prevent weaponization. So there's a nice set of atmospheric lines you could put it at if you wanted to. So we looked at this. All right, so we've never built something like this in space. It's 100 times of the ISS. All right, but you don't need to build this one. You could start with a small one, a class 2 or class 1. The current space PV from ATK is about 0.1 kilowatts per kilogram. We'd like to get this up to 1, which appears to be feasible. It's going to take some work. For reference, the ISS launch mass was over 1 million kilograms. The launch of the ISS is about half that. Launch mass was much greater than that. So 0 to 3 are relatively easy to meet currently. A 4 is not. Okay, where do you put it? We've looked at a variety of things, although this needs a detailed study. Space debris is one of the sort of low-hanging fruits for small systems. A class 1 will take out space debris at 10,000 kilometers. So this is an interesting one for a number of companies. So let me just go through. I'm not going to worry. There's all kinds of issues that I worry about: phase noise and amplifiers, phase shifters, aging, maintaining precision lock, et cetera. I worry much more than you do. So we've done some laboratory testing. Okay, we're going to be doing more. We're looking at orbital configurations with Lockheed Martin and a few other companies. It's completely modular, so you can launch it as a series of stacked pennies, if you will, and build small ones first. And we have various roadmaps we'd like to see implemented. You don't build the whole thing right now. You start with maybe a class 2, which could be put on the ISS to take out much of the space debris that people worry about. You tie into other systems. There's clearly programmatic interest. Since you can modify orbits, it might be useful for asteroid mining. I talk to my friends that like nuclear weapons, who doesn't? And you can use it as a kinetic kill vehicle mode, drive it, because you can get to 1 AU in a few days. So directed energy can provide a solution. It's hard. Okay? It's not impossible, though, I would claim. And I think we should take it seriously and rather just say it looks like science fiction, because it's not. How much is the planet worth? Some days I would say not much. But that's not today. Anyway, I'll end here because I'm slightly over time. And if you're interested, we're trying to collect a group of interested people. So far, we've had quite a bit of interest from people outside. Dick Garwin from IBM has been in discussions with us for quite a while, who asks the hard questions, which is good. The Pentagon, particularly Lieutenant Colonel Peter Garretson, has been working with us. Lockheed Martin's been looking at this. Mikhail Vorontsov at the University of Ohio was part of it, and Jordan Kerr at Laser Motive, and many, many other people. So I'll stop there.